Imagine a playground with a single swing. Only one child can sit on the swing at a time. If many kids want to play, they must wait their turn. A semaphore works like a ticket dispenser that tells a child when it is safe to use the swing. In computer programs, many threads kids share limited resources, swings printers memory. Without a way to tell them when a resource is free, they could try to use it together and cause a mess like two kids trying to sit on the same swing and falling. Semaphores are needed to keep the order, avoid crashes, and make sure every thread gets a fair chance. They turn chaotic access into an orderly line, just like a line at a candy store. Formally, a semaphore is an integer value that can never become negative. Two atomic indivisible operations are defined. P, prob, ren, test, or wait decrease the value by 1. If the new value would be negative, the calling thread must stop, block, until another thread makes it non-negative again. V, ver, hogen, increment, or signal increase the value by 1. If there are threads waiting, one of them is awakened. Mathematically, let S be the semaphore value. P of S, if S is greater than 0, then S becomes S minus 1, else block. V of S, S becomes S plus 1. If any thread is blocked on S, then wake 1. Because the operations are atomic, no other thread can see the semaphore halfway through a change. This guarantees that two threads cannot both think they have taken the same ticket. Explanation: a binary semaphore is a special case where the integer can only be 0 or 1, like a light switch that is either off 0 or on 1. It is often used as a mutex mutual exclusion to protect a critical section, that is a piece of code that must be executed by only one thread at a time. How it works: the semaphore starts at 1 resource free. The first thread that calls P changes it to 0 and enters the critical section. Any other thread that later calls P finds the value 0, so it must wait. When the first thread finishes, it calls V, turning the value back to 1 and letting one waiting thread continue. Typical use cases: protecting a shared variable, for example a bank account balance, from simultaneous updates. Guarding hardware access, such as writing to a disk. Implementing a simple lock around a data structure like a linked list. Real-world analogy: think of a bathroom with a single key. The key being on the hook means the bathroom is free, value 1. When someone takes the key P, the bathroom is occupied, value 0, and anyone else must wait until the key is returned V. A counting semaphore can hold any non-negative integer, not just 0 or 1. It is like a counter that tells you how many identical resources are still available. How it works: suppose we have n identical resources, for example 5 printer slots. The semaphore is initialized to n. Each thread that wants a slot calls P. If the value is greater than 0, it is decreased, and the thread proceeds. When a thread finishes using a slot, it calls V, increasing the counter, and possibly waking a waiting thread. Typical use cases: controlling access to a pool of database connections. Limiting the number of threads that may enter a critical region simultaneously, for example, a read-only cache that can handle 10 concurrent readers. Implementing a bounded buffer where the semaphore counts free slots or filled items. Analogy: imagine a basket that holds 10 apples. The number on the basket shows how many apples are left. Each child who wants an apple takes 1 P and the number goes down. When a child puts an apple back V, the number rises. If the number is 0, the next child must wait until someone returns an apple. The operating system must enforce the atomicity of P and V. Two common low-level strategies are: spin lock, busy waiting, dash the thread repeatedly checks the semaphore value in a tight loop until it becomes available. This is fast when the wait time is expected to be very short because the thread stays on the CPU and does not incur a context switch overhead. However, it wastes CPU cycles if the wait is long. Implementation tip: use an atomic instruction such as compare and swap CAS to decrement the counter only when it is positive. While open parenthesis true close parenthesis open brace int old equals S semicolon. If open parenthesis old greater than 0 and CAS ampersand S old minus 1 close parenthesis break semicolon close brace. Block sleep and wake dash when a thread cannot decrement the semaphore, the kernel puts it to sleep, remove it from the run queue and records it on a waiting list. When another thread performs V, the kernel wakes one blocked thread. This saves CPU time but incurs the cost of a context switch and scheduler overhead. When to choose: use spin locks for very short critical sections, a few nanoseconds, or on multiprocessor systems, where the lock is expected to be held briefly. Use blocking for longer waits I/O operations, or when power efficiency matters, for example on mobile devices. Even with semaphores, programs can still run into classic synchronization bugs. Deadlock: two or more threads wait for each other forever. Example: thread A holds semaphore S1 and waits for S2, while thread B holds S2 and waits for S1. Neither can proceed. Mathematically, a cycle in the wait for graph indicates deadlock. Priority inversion: a low priority thread holds a semaphore that a high priority thread needs, while a medium priority thread runs and prevents the low priority thread from releasing the semaphore. The high priority thread is effectively blocked by the medium one. Real-world: picture a kid with a toy. Low priority is sitting on a seat. A high-ranking kid wants the seat, but a medium-ranking kid keeps running around stopping the low-priority kid from giving up the seat. Starvation: some threads may never get the semaphore because others keep taking it. For instance, if a semaphore always wakes the newest waiting thread, older threads could starve. How to avoid? Use a consistent lock acquisition order to prevent circular wait deadlock. Apply priority inheritance: temporarily raise the priority of the lock holding low priority thread to that of the highest waiting thread. Choose fair queuing FIFO for the waiting list so that every blocked thread gets a turn, reducing starvation. Producer-consumer bounded buffer. We have a fixed size buffer, for example an array of 5 slots, shared between producers who put items and consumers who take items. Use 2 counting semaphores. Empty initialized to buffer size 5. It counts how many empty slots are available. Full initialized to 0. It counts how many filled slots are ready to be consumed. Producer algorithm. Wait empty lock mutex, buffer right equals item, right equals right plus 1 modulo n unlock mutex, signal full. Consumer algorithm. Wait full lock mutex, item equals buffer read, read equals read plus 1 modulo n unlock mutex, signal empty. The semaphores guarantee that producers never overfill the buffer and consumers never read an empty slot. Readers-writers preference to writers. Many threads may read a database simultaneously, but a writer needs exclusive access. Use a binary semaphore resource, which acts as a mutex, and a counting semaphore read count protected by a mutex RC mutex. Reader entry. Wait RC mutex, read count plus 1, if read count equals 1 then wait resource, signal RC mutex. Reader exit. Wait RC mutex, read count minus 1, if read count equals 0 then signal resource, signal RC mutex. Writer simply does. Wait resource, signal resource. This scheme lets many readers coexist, but when a writer arrives it must wait until all readers have left, and new readers are blocked while the writer holds resource. Latency: the time to execute P or V should be as short as possible. Spin locks have low latency for uncontended cases, but high latency when many threads spin. Throughput: the total number of successful operations per second. A blocking implementation may reduce throughput because of context switch overhead, but it can increase overall system throughput by freeing CPU for other work. Scalability: as cores increase, contention on a single semaphore can become a bottleneck. Techniques to improve scalability include queue-based locks, e.g. MCS lock, that give each waiting thread its own node, reducing cache line bouncing. Sharding: using several semaphores for different resource partitions instead of one global semaphore. Hybrid spin then block, spin for a short time then block if still not available, combining low latency with low CPU waste. Memory overhead: counting semaphores need an integer and a wait queue. Binary semaphores are smaller. In embedded systems, binary semaphores are preferred to keep RAM usage tiny. Fairness versus performance: FIFO ordering of waiting threads is fair but may reduce performance because the kernel cannot always pick the most ready thread. Some systems allow configurable policies, fair priority-based or random. In summary, the choice of semaphore type, implementation style, and tuning parameters directly affects how quickly and reliably a program can run on many cores, or on power-constrained devices.